Hi guys, welcome back. This is going to be the second law study guide, so it's going to encompass both F net equals ma, F net equals mv squared over r, and some F net equals 0 because that shows up as well in these type of problems. All right, so the first one, 80 kilogram block is on a frictionless surface. If a force of 24 newtons pulls it to the right, what is its acceleration? So our first step for any of these should be to do a free body diagram. So our free body diagram should consist of a dot, and I have a tension pulling it, I have a normal force that's going up, and I have a weight that's going down. So after I do my free body diagram, it should be obvious to me, in this case, where I have the unbalanced force, and that's going to be in the x direction. So in the x direction, I'm going to say that I have F net equals ma. Because this would be a case of acceleration where something was getting faster or slower. I'm going to take my forces to the right minus my forces to the left. And so this is going to be T equals ma. A is going to be our tension divided by mass. So our tension is 24, our mass is 80, and this is 0.3 meters per second per second. We have to be careful because sometimes they'll give us the mass of the object, sometimes they'll give us the weight. A 15 kilogram block is on a frictionless surface. A force of 20 newtons pulls it to the right. What is its acceleration? How long would it take to travel 100 meters? All right, so now we're incorporating some kinematics after we find out what our acceleration is. So again, I'm going to start with my free body diagram. I have tension, I have a normal, I have a weight. Again, it's obvious to me that my acceleration's in the x direction, so I'm going to do F net equals ma, and I'm going to do right minus left. And so I have T equals ma, so my acceleration is going to be my tension divided by the mass. So in this case, it's 20 newtons divided by 15 kilograms, which gives me 1 1/3. All right, to find out how long it would take to travel 100 meters, I need to make a chart. So my chart is going to be an initial velocity, a final velocity, an acceleration, a displacement, and a time. I'm going to assume that it's starting from rest, because they don't tell us otherwise. I'm going to plug in my acceleration, and I'm going to plug in my distance. So looking at what I have and what I don't have, it seems obvious to me that I should use our first kinematics equation. And so this would be x minus x naught equals v naught t plus 1/2 a t squared. And then I'm going to solve for t. So this cancels out because our initial velocity is 0. I'm going to multiply by 2. I'm going to divide by a, and I'm going to square root. So I'm going to have 2 times 100 meters divided by 1.33 meters per second squared. The meters will cancel out. I'll have 1 over second squared. 1 over 1 over second squared, which would be second squared. So we're going to have units of time, and I get 12.26 seconds. All right, we're going to add friction into this. So when we have friction, friction is going to be the thing that's going to make us have to deal with the y direction too of the situation. So we're going to have to use the y direction because friction is the connector between the normal force and mu. So again, I'm going to look at my free body diagram. I'm going to assume that the tension is greater than the friction. But it could be the other way around. And so again, my unbalanced forces are going to be tension and friction. I'm going to do F net equals MA in the x direction. I'm going to do rights minus lefts. So this is going to be T minus F equals MA, and A is going to be T minus F over M. And I'm going to plug in my T and my F. The only problem is I don't have the friction. I have the coefficient of friction. So I can't just plug in this 0.2. This isn't the force of friction. This is the ratio of how hard it is to pull something to how hard it is to lift something. So the relationship between these when they're sliding is that the kinetic friction is equal to the coefficient of friction times the normal. Well, the normal is a force in the y direction. In the y direction, even though I'm accelerating in the x direction, things are still balanced. So I'm going to do the y direction. I'm going to do F net equals 0. I'm going to do up minus down. So I have normal minus mg is equal to 0. So my normal is equal to my weight, which is often the case when we're on level ground. So again, they give me the mass, so I need to multiply it by 10 to make it a force, to make it a weight. So this is going to be 1.2 times 10 gives me 12 newtons. I'm going to plug this in for my kinetic friction. And it looks like my kinetic friction, 0.2 times 12 would be 2.4. So now I can plug it in. I have a tension of 24, I have a friction of 2.4, and I have a mass of 1.2. And again, this should be in parentheses on the top. You don't want to do this minus this divided by that in your calculator without the parentheses, because you'll end up just having this minus the fraction of those two. And this is going to give me an acceleration of 18 meters per second per second. All right. A 2 kilogram block is on a frictionless incline of 37 degrees. What is the block's acceleration down the incline? I have a picture here of what my block looks like. So if I do my free body diagram, weight is still straight down, and normal would be perpendicular, and that's it. So in this case, the weight is both balancing the normal and it's accelerating it down the incline. So I want to break that weight into components. So what I'm going to do is I'm going to take this, I'm going to pick it up, and I'm going to spin it so that the normal is straight up. And my weight is the only thing at an angle. And then I'm going to draw in the components of weight. Now the angle of our incline, which is always the lower angle, 0 would be a level road and it goes up from there, is 37 degrees. That angle is this angle, the upper angle. If you're unsure of why that is, you can go back to my video where I prove it with geometry of how that angle is the upper angle. So that's going to make the arrow that I'm interested in, this component, because this is the one going down the incline, mg sine of 37 degrees, because this would be the opposite side. And so down the incline, I'm going to make positive, and I'm going to say F net equals MA. And so this is going to give me mg sine of 37 equals MA, so A is going to be g sine of 37, which ends up being about 6. We did this in the lab, obviously not at a 37 degree angle, because 6 meters per second squared is a ton, but we did, I think, 2, 3, and 4 degrees on an incline. And then we timed it and we checked the acceleration that we saw for kinematics with what it should have been based on our F net equals MA. All right, now we have friction on it. So again, I'm going to look at my free body diagram. I'm going to have normal going normal. Normal means perpendicular. I'm going to have weight going straight down, and I'm going to have friction going up the incline. So the friction is going to oppose the motion or the perspective motion. And in this case, we have motion. I'm going to rotate my free body diagram. And again, I'm interested in the components of the weight. And once we introduce friction, I'm going to have to deal with the y direction. So I don't have to get normal. I know this. And again, this is 37 up here, which is the 37 down there, which means down the incline, I'm going to have mg sine of 37. And perpendicular to the incline, I'm going to have mg cosine 37. All right, so I'm going to solve for the normal right off the bat because I know from the previous problem I just did a couple problems ago that I'm going to need it anyways. So I'm going to say that perpendicular to the incline, F net's equal to 0. And so I'm going to take my forces up minus my forces down, which is going to be n minus mg cosine of 37 is 0. So the normal is going to be equal to mg cosine 37. I'm going to plug in my values. M is 2. G is 10. And cosine of 37. First time I'm using this so far, so I should make sure that I'm in degrees for this. And I'm going to have 20 cosine 37. 16, pretty much. So my normal is going to be 16, and I know that my kinetic friction is mu times this. So I'm going to plug in the 0.15, which is this coefficient of friction. And I get a force of friction of 2.4, which is weirdly the same one we got previously in the last problem. All right, so down the incline, I'm going to have acceleration, and it's going to go this way, so I'm going to make that my positive direction. So I'm going to say F net equals ma down the incline, parallel to the incline, in the direction of the incline. And so down the incline is this mg sine of 37. Going up is F, friction, and my acceleration would be mg sine of 37 minus F all over M. So this is going to be 2 kilograms times 10 meters per second squared times the sine of 37 minus 2.4 all divided by 2. And this gives me an acceleration of 4.82 meters per second per second. I'm going to check that in the calculator. I don't think there's any errors on this, but this is not something I can do in my head. At least not this early in the morning. Yep, 4.818. All right, now to find out how far or how long it takes, I need to make a chart. And I want it to go 4.82 meters, which seems like a weird distance. I don't know why that is. I don't remember. Again, I'm going to assume it goes from rest. And my distance is the same as the acceleration. I guess that's what I was getting at. Again, same formula. X minus x naught equals v naught t plus 1/2 at squared. That cancels out because v naught 0. I'm going to multiply by 2. I'm going to divide by a, and I'm going to square root. And since my displacement and my acceleration are the same, I'm going to end up with those canceling out. And I'm going to end up with radical 2, which is 1.41. All right, number 6, a force of 12 newtons directed 40 degrees above the positive x-axis, acts on a 10-newton block on a frictionless surface. What is the object acceleration? How long would it take to reach 25 meters per second? All right, so here's our picture up here. So my free body diagram should have a tension, and I'm allowed to have this angle in here. That was a question on the previous pre-lab. Was, am I allowed to have the angle on a free body diagram? Yeah, you can. The things you can't have are components, because they're not real, acceleration, velocity, because they're not forces, and F net and centripetal force, because they're not individual forces, they're combination of forces. All right, so I have to do this separately, and I want to get Tx. So this is my adjacent side. This is going to be T cosine 40. So in the x direction, F net equals ma. I can see that. There's no other force acting there, right? So I'm going to have T cosine 40 equals ma. So A is going to be T cosine 40 divided by m. So this is 12 cosine 40 divided by, oh, they got us here. It's a 10 Newton block. So the weight is 10 newtons. So the mass would be 10 divided by g. So if g is 10, 10 divided by 10 would be a 1 kilogram block. All right, so this is going to give me an acceleration of almost 9.2. I want to know how long will it take to reach a certain speed. That's a little bit different. I'm going to say that my initial velocity is 0. I want to get to 25. I know my acceleration. And I want my time. All right, I'm going to use the second equation. And I know that V is equal to the initial V, V naught, plus AT. And so V minus V naught over A will give me T. So my final velocity is 25 minus my initial, which is 0, divided by almost 9.2, gives me a time of 2.72 seconds. All right. 0.05 kilogram B flies. It's attached to a string and flies in a horizontal circle of radius 0.5 meters. It takes the B 1.5 seconds to travel once around the circle. What is the B's velocity, centripetal acceleration, and tension? All right, so in uniform circular motion, motion where you have a set radius and a set speed, our speed is a special speed because it is the circumference, which is 2 pi r, divided by the period, which is the time for one cycle. So my 2 pi r is 2 pi times 0.5, just like we did in the lab, divided by 1.5 seconds. And this is giving me a speed of 2.62. In circular motion, we also have a special acceleration because we're not as much interested in how the velocity arrow is getting bigger or shorter, but just how it's turning. And this is given by v squared over r. So I'm going to have 2.62 meters per second squared divided by 0.5 meters. That's a square. And this is going to be 13.7 meters per second squared. This B, if I look at the free body diagram, has a tension going towards the center, and it also has its weight and some kind of lift force that's lifting it straight up, but it also has a force that's going that way I'm not going to worry about. So this is our centripetal force, our F net for when our direction is changing is F net equals mv squared over r. I take the forces towards the center minus away. I just have a towards. So remember, we don't need an away. Circular motion requires something that's turning it. It doesn't require something that's trying to keep it from turning. And so my mass of my B is 50 grams. So I have 0.05 kilograms times our centripetal acceleration, which is 13.7 meters per second per second. And I got 0.685. So that's how much tension would be in the string to turn it. All right, now we have a vertical circle. This is different because in a horizontal circle at constant speed, your tension is going to be constant. That's not going to be the same in a vertical circle. So we're going to look at our circle here. I have a spot at the bottom and a spot at the top that are of interest to me. When it's at the top, there's going to be a tension going down and a weight going down. And when it's at the bottom, there's going to be a tension going up and a weight going down. So gravity is always going to go towards the center of mass of the Earth, but tension will go depending on how the rope is directed. Oh, they want a horizontal one too. I need to add an extra dot in there. What a twist. Okay, so top. F net equals mv squared over r. We take forces towards the center minus away. This is going to be T plus mg equals mv squared over r. So T is going to be mv squared over r minus mg. So this is 0.25 kilograms times 3.61 meters per second squared divided by 1.3 minus 0.25 times 10, which would just be 2.5. Check my work. And I got 0.006. That's essentially 0. All right, bottom. So the tension's going to be more at the bottom because the tension's going to have to do two things. It's going to have to lift the block and it's going to have to turn the block. So I'm going to take my forces towards the center minus away. So I have T minus mg equals mv squared over r. So T is going to be equal to mv squared over r plus mg. So this is 0.25 kilograms times 3.61 meters per second squared divided by 1.3 plus 2.5. And so this is 5. Then the last one is going to be our side view, horizontal one. And in this case, the weight is neither helping us nor hindering us. It has nothing to do. It's perpendicular to the center of the circle. So when I do my towards minus away, I only have tension. So when I plug in my 0.25 times 3.61 divided by 1.3, I just get 2.5 newtons. So that makes the vertical circles a little bit more complicated. But the free body diagram should help you in all cases. All right, 1,000-kilogram truck takes a 200-meter turn at 35 meters per second. What must be the minimum coefficient of static friction between the road and the truck to keep it from sliding? What is the force of friction that keeps the truck on the road? So again, if we're looking at this, here is the front of our truck. And if this is my center of my circle here, the forces on this truck are the weight of the truck, the normal force on the truck, and then the static friction on the tires that are pushing it towards the center. I want to get some headlines. All right, so I know if friction's involved, I have to get the normal. So I'm going to say in the y direction, F net equals 0. And I'm going to take my forces up minus down, so that's N, minus mg equals 0. So the normal is equal to the weight. If we're on level ground, that's often true. So this is going to be 1,000 kilograms times 10. And this gives us 10,000 newtons. All right, now I need to find out how much friction I want to make this turn. And so the friction going towards the center is changing the direction of it. So in the x direction, I have F net equals mv squared over r. So I'm going to take the forces towards the center minus away. And as often is the case, there's only towards the center. So this is going to be friction equals mv squared over r. The mass of the truck is 1,000 kilograms. The speed that he's maintaining is 35 meters per second per second. Sorry, 35 meters per second, and that's squared. And our radius is 200 meters. So this ends up being 6,125. Now the minimum, and again, static friction is as much as it has to be. It has to at least hold this true. It could be more, and that would make it safer. But there's a limit. And so it's the ratio of the friction to the normal. So it has to at least be 0.625. Usually rubber on concrete, dry concrete's around 1. So this truck could easily make this turn at that speed. All right, guys. Well, good luck on the second law test. Remember, there'll be some first law stuff on there and some conceptual questions.